It now gives me pleasure in introducing our speakers tonight. You will see we have three speakers. Starting us off will be Gillian Browning. And Gillian is a fellow of the Institution of Structural Engineers and has dedicated the past 20 years to specialising in the design of structures subject to dynamic loading. Her extensive portfolio includes large stadia, performance venues, commercial and residential projects, as well as low vibration laboratories and research facilities. She also chairs our iStructE technical panel for seismic and dynamic events and is actively involved in the working group revising the ISE publication on the dynamic performance of grandstands. So she's very busy. Gillian is passionate about improving vibration serviceability design to facilitate effective low carbon building solutions. We'll then be followed, Gillian will be followed by Will, and Will Pern brings over a decade of experience in the engineering industry, having worked across diverse sectors. His significant experience in the design, assembly and fabrication of special structures such as art pieces, theatres and sculptures, often utilising innovative materials. Alongside his work on special structures, Will is also proficient in conventional building structures, delivering projects from conception to construction. Last but not least, we'll have Camilla Ribolato, and she has extensive experience in structural design for a variety of construction projects, ranging from small to large and complex, with a focus on concrete and timber. She specialises in wind design for high-rise buildings, including studies on vortex-induced vibration and lateral acceleration. Additionally, she conducts dynamic analysis of light timber floors, providing verification and recommendations for optimal solutions. So as you can see, we have three excellent speakers for you tonight.
Right, so Matt gave a bit of an introduction, but I thought I'd just add a little bit to that, a bit about my history. So after graduating, I started working on refurbishment projects at Alan Baxter's in London. So at that point, I was doing lots of lightweight and timber solutions, albeit 30 years ago. I then moved to Bure Happel to work in the Emirates Stadium in 2001. And from that work, that piqued my interest in dynamics. And so then I went off to Bath University and did a PhD on the human perception of vibrations in grandstands. And then, as Matt said, ever since then, I've been developing Bure Happel's capabilities in structural dynamics. And I've covered everything from like performance venues with like crowds of people jumping around to science labs where you don't want to feel a pin drop. So my real passion is for dynamic analysis and showing how, if we understand how a structure behaves, we can then use that to maximize the performance and efficiency of the design. So what all three speakers here are to talk about today is what I call vibration serviceability. And by that, I mean ensuring the comfort of the users of the building or the structure in everyday use. So we're not talking about life safety or failure issues. We're focusing on low levels of vibration, which sometimes will be large enough to be perceived. And what we're aiming to do through our design is to avoid those type of small vibrations becoming large enough that they disturb the occupants. For example, stopping them from sleeping, or maybe something we've all felt, perhaps wobbling their desks so they can't focus on their work. So this is a summary of what we're going to be covering today. I'm not going to apologize. The subject matter is very technical, and I do appreciate that the audience will include a wide range of experience levels. To be as inclusive as possible, I'm going to start with a general introduction on the basics of vibration analysis, so that when we move on to the interesting stuff regarding the lower carbon solutions and things like that, everyone can follow along. So the plan is for me to do this technical introduction, and which should last about 20 minutes. And then I'm going to hand over to Will and Camilla, who will showcase some real life examples of vibration serviceability and sustainable design. And then I'll come back in and I'll finish off with some thoughts as to where we're heading in the future. So now, because we're carrying on a quite tight time schedule today. I will be following my notes quite closely so that I try not to miss any key points, and also hopefully that will stop me going off piece, which I do have a habit of doing. So, right, let's get started. Right, so hopefully most of you will be familiar with this I-struct-T diagram, the hierarchy of net zero design. It shows graphically the most effective means to lower carbon in our structures. So you can see here this big use less stuff. And then this can be done by harnessing the ideas shown on the right-hand side. So if we look at these concepts with respect to design of floors, they can be condensed crudely into these three categories: build thinner, build lighter, and build using carbon neutral materials. And this is this aspect of sustainability with a focus particularly on floor design that we're going to explore today. Right, so if we start by looking at the relative weights of some common floor solutions, you can see that the concrete frame solution in the grey is generally about 50% heavier than the steel concrete composite option. And then if you look on the right-hand side, the timber alternative, which I've allowed for a granular fill and some fiberboard for a fire and acoustic system, the total weight of this timber system is less than half of that of the concrete solution and about 2/3 of the steel concrete composite option. So I think the key message to take forward as we go through the talk is that timber solutions are significantly lighter than the flooring systems that are generally covered in the current vibration performance guidance guides. So the SCI P354 guide and the Concrete Centre's CCIP 016. I was going to add an embodied carbon row to the bottom of that table, but after starting to do it, it proved too hard because there were just so many factors involved that influence numbers. But effectively, the take-home message is that the embodied carbon of timber is notably lower than the more traditional options of concrete or composite. So, right, so we're now going to dive into the technical stuff. We're going to start first with the basics of dynamics. So everything has its own inherent mode of vibration, be it a floor or bridge, parts of your car, or as can be seen here, guitar strings. These modes of vibrations are how the structure will choose to vibrate when it's hit with a single impulsive force. For example, if you tap it with a hammer or you twang the string as shown in the GIF. So each of these modes has its own natural frequency of vibration, so how many cycles it vibrates every second. And it also has its own shape of vibration. And I think hopefully the GIF shows both of those things quite clearly. But in addition to that, there's a third thing, which is the mass associated with that shape of vibration. One of the key concepts of dynamic response is resonance. Resonance is where an external dynamic force is at the same frequency as one of the modes of vibration of the structure, and repeat application of this external force causes a greatly magnified response. So a good example of this is a playground swing. And we all know from being children, in order to make that swing go higher and higher, the thing to do is to throw your weight forward when the swing moves forwards, and then to push your weight backwards as the swing moves back. So here what we're doing is allowing our forcing to follow the natural pendulum motion of the swing and thus amplify the response with every pass. And for those that would like a slightly more scientific definition, I've got one here for definition of resonance. So I'll just give you a minute to read this through. And then there's a second part as well, which I'll just bring up now. Hopefully I'm not going too quickly. Okay, so hopefully we've managed to assimilate that information. So what I'm going to do now, we've got this understanding of resonance, is to explore what that looks like in real structures. So I'm going to start here with this model of 4 rubber balls, which have been mounted on timber dowels. We can imagine these as, for example, tower blocks being excited by the wind, or if we rotated it through 90 degrees, as perhaps cantilevers with people walking on them. So I'll just start out by explaining the principles of the model. All 4 balls are the same size and have got the same mass. The left-hand dowel is thicker than the rest. It is 10 millimeters in diameter, whereas the other 3 are only 6 millimeters in diameter. 2 of the dowels are the same length. But most importantly, all 4 stick structures have different natural frequencies. The man on the left is moving the base of the device at varying frequencies. And so when this excitation frequency matches the frequency of one of the sticks, you can see that it clearly resonates and it moves with a greatly amplified response. Then as he changes the excitation frequency, that ball will vibrate less. So for each key excitation frequency, only the stick whose frequency is being matched oscillates madly, while all the other sticks remain largely still. This is another key concept of dynamic analysis. When a structure is excited at or close to its natural frequency, you'll get a magnified resonant response. But if it's excited at a frequency away from its natural frequency, the response will be considerably smaller. So this concept is also shown very clearly by this graph, where the resonant peak occurs when the excitation frequency matches the natural frequency. But away from this peak, so to the left and right of the graph, there is no magnification. The magnification of the resonant response is largely influenced by the damping of the structure. Structural damping is usually very low, between about 0.5% for bare welded steel structures like stairs, up to about 3% for a fully fitted out building. This peak value varies as 1 divided by twice the percentage damping. So a typical floor with 2% damping has a maximum dynamic magnification factor of 25, which you can see here in the graph. That is, the resonant response is about 25 times the static response. This highlights why to prevent resonance is often a key goal of engineers. So we discussed the modal properties and found that all structures have their own inherent modes of vibration, characterized by mode shapes, natural frequency, and a modal mass. But each structure will have multiple modes of vibration. Take, for example, this simple bridge. Mode 1 is likely to look something like this, and mode 2 like this, but at a higher frequency than mode 1. And then we have mode 3 like this, which is a natural frequency higher than both modes 1 and 2. But why is this important? Well, the overall response of a structure to a dynamic load will be the sum of the responses of each of these individual modes of vibration. And this is what's called modal superposition. Right, so now we have to take a slight leap forward in order to fit everything into the allocated time slot. So if afterwards, going back and thinking about things, you feel like you'd like to understand this section a bit on loading a bit better, I suggest you read the relevant chapters of the UK design guides for floor vibration. So I mentioned these before. There's the SCI guide P354 and the Concrete Centres guide CCIP 016. Right, so now back to the slides. So what we look at here is a breakdown of the dynamic force due to walking. And that force is shown by the dark blue line. So either here on the 3D view or here on the 2D graph. Right. This slide has got a lot of information on it, but really the key thing to take away from this is that the loading is periodic, so it repeats itself at a particular frequency. And because of this, it can be broken down and represented as a series of sine waves. So that's what can be seen in the 2 graphs here. Now, these smaller sine waves are components called harmonics, and they occur at multiples of the walking frequency. So the first harmonic component matches the walking frequency. The second harmonic is at twice the walking frequency, and the third at 3 times the walking frequency, and so on. So this next graph then shows the relative magnitude of these harmonic components of this walking force as we use it in the UK. And it also shows the frequencies over which these components act. So each harmonic component varies with the frequency of the walking. So effectively, the faster a person walks, the larger the magnitude of the force they impart. What you can see clearly from the graph is that the second, third, and fourth harmonic components are quite similar in magnitude, although the second harmonic component is slightly larger. And critically, if we look at the left-hand side of the graph, what you can see is just how large that first harmonic component is. And so if we had a resonant response due to that part of the force, it would be really, really big. And that therefore, that's something we really want to avoid at all costs. So that's why when you look at design guides, there's normally a minimum floor frequency given. And this just see, if you see here, that's given by the kind of thick black line on the graph. And that minimum floor frequency effectively just avoids resonant and off resonant responses due to that large first harmonic component. So I've just mentioned off resonance. So what exactly is that? Well, what I mean is that if you have an excitation close to the natural frequency, so for example, at the place where the arrow is shown on this graph, you can still get quite a significant resonant response. And this is because, as we mentioned before, this peak is based on how much damping you have. And because structures have very low damping, this peak is quite steep and the sides are quite steep. So you can still get, even if you're not quite bang on matching your frequencies, you can still get quite high resonant response. Okay, so hopefully by now we understand a bit more about resonance and the dynamic forces due to walking. So we'll just take a second just to think about the form in which we're going to assess any vibrations that are being generated by this walking force on our structures. So for humans and for human comfort, acceleration levels have been shown to be the most accurate predictor of tolerance, although perception is individual and everybody's different. Some people are far more sensitive to vibration levels than others. I think over time I've become more and more sensitive. So I'm now one of the most sensitive people I know and can't cope with any vibrations at all. So if we just now move on to looking at how, well, we now know that we want to look at accelerations in order to assess a vibration, but how are we going to do that? So what we've got here is the formula for calculating accelerations in a structure due to resonant excitation. So where you've got components of your excitation force which match closely to one or more of the natural frequencies of the structure. So using this formula for assessing resonant vibrations as accelerations, the key components we can see are the first one here, mu. That is to do with the location. So obviously, if you're in the middle of a floor, it will be more bouncy, more responsive than if you're close to a column. Then we've got the walking force, which we described previously. And then the next one along is this dynamic magnification factor. So again, we've seen this graph before. This dynamic magnification factor encompasses how close your excitation is to that peak, and also how tall that peak is. So that, again, that's dependent on the damping. And the final factor, which we haven't mentioned here, but this one is so important, is the mass that's involved in that particular mode of vibration. So as you can see where it is on the bottom of that equation, the greater the mass, the harder the floor is to excite, and hence the smaller the vibration and the acceleration. So if we're trying to compare vibration serviceability of various different types of floors, the key factors for that resonant response are the mass and the damping. This is given that the harmonic loading components for the second, third, and fourth harmonics are all relatively similar, as we saw in the graph before. And we've already said that we're going to make sure we design to avoid that large first harmonic component. Right, so if we then remember back to that table with the 3 material solutions we discussed at the very beginning of the presentation, where there were considerable differences in weight between the options. We now understand that those differences in weight may translate to how those structural systems will then perform under dynamic loading, given how crucial that mass is to determining the magnitude of your vibration. So what we see here is we've got a graph which compares what the predicted resonant response would be for structures with a natural frequency given on the x-axis. We've got 3 different modal masses which have been assumed, representing the 3 material solutions described in the previous slide. So we've got grey for concrete, the blue for the composite, and the green representing the timber. So the mass ratios of these assumed structures are, as per the table, they're in the same relative mass ratios. So the heaviest is the concrete and the timber is the lightest. So if we then just look at the grey concrete line along here, we can see how the performance of a 4 Hertz structure down here will compare to that with an 8 Hertz structure here with the same mass. So you can see how this shape closely resembles that difference in the forcing components of the second, the third, and the fourth harmonic components. And literally that is all the difference between this edge of the graph and this edge of the graph. Okay, but then if we start to look at the different lines, so the blue and the green lines, which represent the composite and timber structures respectively, we can see how that difference in mass has an influence on how those systems perform. So we've got the timber solution, which has got less than half the mass of the concrete. So therefore, this resonant response up here is more than double that of the concrete down here. So this inherent lack of mass is a critical factor when we're proposing lighter, more sustainable flooring solutions, because if all other factors are equal, these lighter floors will show a much greater resonant response than your traditional heavier weight solutions. Right, so that's resonant response. So that's what we've talked about so far. But then, well, what happens to floors beyond this zone? Right, so effectively, what we're going to look at now is we've seen that this resonant response occurs over this portion of the graph, so between your sort of 3 Hertz and 10 Hertz. But what we need to look at is like, well, what about this zone? What happens here? And that's what we're going to look at next. Okay, so this zone, this high frequency zone, is where the transient or impulsive response comes into play. Okay, and so this is a response of a high frequency floor when you hit it with, for example, either a hammer or from a single heel impact from walking. And this impulsive force excites the floor and causes it to vibrate at its own natural frequency. And then it decays over time until the next heel impact pulse causes it to vibrate again. So each of these spikes is as a heel impact. You can see it's vibrating at its high frequency until it's then decaying with the damping until it's hit again. So this is a graph that's available in the SNI guide. But I also thought it'd be nice to give a real life example. So this slow-mo video of a springboard shows the extreme of what's happening on the floor under an impulse loading. So when I press play on the video, if you watch that central diving board, so this one here, carefully and see that what happens every time the girl's feet leave the board. And you'll see the board vibrate freely, and each time it vibrates in a similar kind of pattern every time. And that pattern is a combination of the mode shapes of the diving board, which are inherent modal properties of that board. So here we go. Let's try and see if this video works. So we can just see as she lifts off, see how the board vibrates. And then she excites it again by jumping on it. See, it's a similar sort of pattern, this high frequency waggling around on the board. And then it'll do it one last time when she hits it again. There we go. Okay. So we're going to do the same breaking down of the formula. And as for the resonant response, it's the acceleration we're interested in. Acceleration, magnitude of this vibration, so that we can judge the human response to this impulsive or transient vibration. So if we start by going through all the different factors, so again, you've got this same location factor, and then this time your force, it's here, the force is the dynamic force due to the impulsive force. And what you can see is it's a ratio between the walking frequency and the natural frequency of the floor. However, in the overall formula, this force is always multiplied by the natural frequency of the floor. So you can see, if you remember back to your days, your maths lessons, that by doing some crossing out and assuming things get really quite small, you can effectively say that, well, actually, all of this can be sort of simplified to it varying as the walking frequency. There's also this term here in the formula, which relates to the damping of the system, but actually, again, going back to the fact that we've mentioned that actually structural damping is always very low. Actually, this factor doesn't change very much at all, so we can kind of ignore that. So finally, there it is, the big mass component. So again, mass is really important. And as it's on the bottom, the greater the mass involved in the system, the lower the acceleration. So then summarizing the key factors defining, that acceleration due to an impulsive or transient excitation, mass is key when you're looking at flooring options, so similar to before, and that's because your maximum walking frequency is likely to be set by other factors, and it will usually be consistent across, the three or so options that you're considering. Okay, right, slides are slightly sticky again. Apologies.
The sticky slides just give us time to catch up.
Right, sorry again. I'm going to try shutting it, and then and as soon as I say stop, it decides to play. Right, okay. So what we've got here is that transient response plotted in the same way as we did for the resonant response with the 3 structural material options. So you can see we've got the concrete in grey, the composite in blue, and then the timber in the green. And what this graph shows is that as the natural frequency of the structure increases, there's only a slight reduction in the predicted acceleration, particularly in this sort of zone, where we're actually focusing on these types of vibration. And so, as before, because we mentioned, this mass playing a really, really large part in this calculation, you can see that the much heavier concrete solution is outperforming both the lighter composite, and then the much lighter timber options. Okay, so what I've done now is I've added back in that resonant response, so we can just see what happens to, or what the maximum response would be to a structure over that full frequency range. You can see how at those lower frequencies, it is the lower structural frequencies. So this is for sort of floors that have got frequencies between about 3 and 9 hertz. It's that resonant response that's dominating. But once you get up here, so you've got floors that are above 10 hertz, in that zone, it's a transient response that's greater. Now, this switchover point is actually determined by what you take as your maximum walking frequency. So in this case, I've just happened to have set it at 2.2 hertz. I could have set it at something else, but I just happened to choose 2.2. So I've tidied up the graph and to create this kind of combined graph, which as I mentioned, it shows, the lower frequency structure has been dominated by that resonant response, and then the higher frequency structures being where the transient is more critical. So what's really clear here from these graphs is that there's this very large drop-off, particularly on the lighter structures, between this resonant response here and this transient response further on. And that's something that's going to be utilized very strongly in the next section of the presentation. So we are getting there. We're getting through it. Right. So we're now going to look at how lightweight floors have been designed up until now. So we're going to take that foundation knowledge that I've just talked you through and see how that's been used up till now in the design of lightweight floors. And when I say lightweight floors, I'm talking about lightweight floors such as the one shown here. So you've got pressed steel joists supporting a timber decking. And those type of floors are covered in Chapter 8 of the SCI P354 guide. But we're also going to talk about timber floors designed to the 2014 edition of Eurocode 5. So both those design guides advise designing lightweight floors as if they were high frequency. So effectively it was saying you should design these floors so they only exhibit a transient response because you've got this big resonant response here because of this big drop off. Yeah, so you can see that particularly for the lightweight floors. So here we've got the timber in green and the concrete again in grey. You can see that particularly strongly for these lightweight floors that there's massive drop off due to this lack of mass, so that you get a very high resonant response here, which just means that these lightweight floors just cannot compete and provide the same level of performance as a much heavier, for example, concrete solution shown here. So using these guides, a damping value of about 2% would have been used, similar to that used for concrete and steel composite options. However, when we looked at formula for the resonant response, there were two key factors. There was the mass, but there was also the damping. So what would happen if we change that damping value for these lightweight floors? Well, please work slides. The next iteration of Eurocode 5, which is available to view as a working draft, does have an updated vibration section. And this is much more extensive than previously, and it's been extended to include offices as well as residential buildings. Now, one of the key changes is this inclusion of some additional higher damping values for timber floors with a floating floor layer. So I've just copied and pasted it here. The draft EC5 code says that where you've got floors with a floating floor layer, you can get a damping of up to 4%, compared to the 2% damping, which was assumed in the UK National Annex of the 2014 version. So if we think about modern timber floors, quite often a floating floor layer is relatively common because the floors are lightweight and they're flammable. You tend to have acoustic and fireproof layers added into that system to make their performance, their serviceability under that acoustics and fire suitable for their use. So if we look at what happens to our graph, so we're back to the same graph, and we change the damping of that timber floor from 2% to 4%. So we're just doing what's suggested in the draft EC5, that it's got a floating floor layer. And we can see that change in the resonance section of this graph is the same as doubling the mass, which we could tell from our formula. But then it also puts this timber floor performance so much closer to that heavier concrete solution. And so the consequence of that is that in designing that timber floor to meet an agreed response, it becomes much, much more achievable within this resonant zone compared to what you would have been trying to do if it only had 2% damping. So That 4% damped floor can have a much lower frequency, so it can be much more flexible and use less material than a 2% damped timber floor in order to meet a specific acceleration limit. So what I'm going to do now is just explain that using an example. So if we say that our response factor limit was 8, so you can see this line going sort of bang across the middle of the graph. So if we had a lightweight floor with 2% damping, based on this graph, you'd have to have a minimum frequency of that floor of about 9 hertz in order to meet that response factor of 8. Okay, but if we said we had a lightweight floor with 4% damping, so we've got the same mass, same floor, but we've got 4% damping. If we just change that damping, we can then see that this resonant response, the whole of that now falls below our response factor of 8. So that means we could potentially use a floor with a frequency of as low as 3 hertz. So that is effectively 9 times less stiff than this lightweight floor with 2% damping. And that would equate to a fairly significant carbon saving. So I'm now going to hand over to Will and Camilla, hopefully they're ready, to showcase some of our recent projects. These are ones where lightweight solutions were required, where vibration serviceability became a dominant design factor, and where significant carbon savings were made through collaborative design. So thank you all for listening, and now over to Camilla and Will.
Thanks, Gillian. So just as a quick kind of reintroduction, I'm Will. I am an associate within the London team for Bureau Hapag for structures, and today I'll be looking through 2 case studies and the importance of vibration serviceability had on sustainability of the design process. So both the case studies that I'm going to present are in London. They're both reuse and refurbishment jobs. So it'd be worthwhile just kind of touching on this net zero design hierarchy. So as mentioned before, in order to kind of, minimize the amount of embodied carbon that we're putting out into the world, we kind of need to use less stuff. So it's important that we try and reuse and refurb existing building stock where we can. And what does that mean? So if you're looking at buildings, say in London, it's, a client says, oh, I've got a building that's 5 stories, but I want 6 or 8 or 10. If we want to try and reuse that, we need to keep the loads that we're putting on the building within the existing capacity of the structure. That allows us to minimize strengthening and potentially reuse foundations. So how that ends up working in practice. So the first case study is a office in Mayfair, which was it's a London refurbishment project, basically. And this building was an existing building which utilized some retail, and the client wanted to add 5 new floors to create a new building which had 2 floors of retail and the rest remaining office. The project is currently on site, and the ambition was to make it as sustainable as possible when trying to reduce embodied carbon. So we were looking at trying to minimize any weights that we put back on the structure in order to reuse foundations and minimize strengthening again. As such, CLT floors were used as a result of being lightweight, which helped us keep the loads down. The client also asked for the building to be PCO compliant to 29 spec, which is often a clause or requirement or request from clients within London, as it allows it more easy for them to let to future tenants. So this building, CLT floors. So as Gillian mentioned before, CLT is both lightweight, has its issues with dynamics. Also, CLT is flammable and doesn't provide as much acoustic insulation. So to overcome these, you add performance layers that often come in the form of fireboard and acoustic layers, which can allow an increased level of damping that can be assumed within the design as a result of this, as per the work in progress timber Eurocode. And for this project, a response factor of 8 was actually targeted as per the BCO specification, which there are probably conversations to be had whether or not how applicable that is for lightweight structures. So on to the dynamics of this project. So the floor is driven by dynamics rather than ULS or SLS statics on the nature of the lightweight floor and spans. So the first vertical mode of the floor is about 10 Hertz. It can be considered a stiff floor. In the final design, the floor response is driven by transients. And one of the first things that we looked at was the impact of actually increasing the damping on the floor. So from the previous build up, you have quite a lot of performance layers. So 4% damping could actually be justified. And that allowed us to reduce the response factor from 35 to 20. So it brought us a long way there, but still quite a way to go to 8. So one of the next things that we looked at was, this is an office. It's kind of, it's an office. So how fast are people going to walk in an office? Initially, we were assessing the floor up to 2.5 Hertz. 2.5 Hertz works out about 6 kilometers per hour walking speed, assuming about 0.7 meter stride length. So it's quite fast. And I don't think many people work in offices generally at that speed. Circulation areas such as corridors, yes, but not typically around the offices. So we then start looking at what happened is if you reduce the frequency, and it basically allowed us to bring the transient response down to 8, just below 8 for all of the office areas. As per the parameters highlighted with Gillian before, the transient vibration or etc. response factor would be driven by the mass and the frequency. We couldn't increase the mass because it would start going against the whole point of sustainable design, where we're trying to minimize weight to reuse the building. So we had to actually genuinely look at the frequency and think what was viable and accurate. The second case study that I want to discuss is Gresham. So Gresham is slightly more conventional than the Mayfair office. So it is the redevelopment of an existing building, again, where we've added 4 new floors on top. The project's currently in REBA 4. The client also wants a BCO specification because it makes it easier for them to let to a tenant. And again, wanting to hit a response factor of 8. Spans are about 13.5 meters to match the existing grid, which from my memory was also done to a previous version of BCO. The slabs are lightweight composite deck, and that was chosen to minimize strengthening and to allow for reuse foundations. CLT was considered for the scheme, but it was ruled out as it actually resulted in heavier floors because of how thick the CLT had to be to get the spans to work, and also extra complexities such as fire and insurance and acoustics. So as such, they went with a lightweight composite deck. So this team, during all of the design development, they've always been looking at dynamics, and as the floor plates have been entirely driven and sized for dynamics, because that is the driver, it's not SLS or ULS statics. It has allowed them to be in a position going to REBA stage 4 where they've been able to highlight areas where the floor is overperforming the response criteria for the client, and has allowed them to actually start tailoring their scheme to try and minimize steel tonnage and help reduce embodied carbon. Which just highlights the importance of early consideration for dynamics for potential reduction in material when looking at lightweight floors, and this is increasingly prevalent within reuse and refurbishment jobs. Thank you very much. I'll hand you over to Camilla.
Thanks, Will. So, hello everyone. As my colleagues, I'll quickly go back again.
Camilla, I'm not sure if you're hearing me, but it seems like you're a bit stuck for us at the moment.
Do you hear me?
Yes, I can hear you now, but I can't see you yet.
You can. Should I reload or?
Let's wait for a sec. Yeah, you appeared. That's perfect.
Okay, thanks. Sorry for that.
No
I
problem.
for me it was showing normal. I might reduce here the quality as we talked before. Yeah, is it working?
Yes, that's perfect.
Okay, perfect. So yes, I was as was saying, I'm working in some light floor analysis, vibration, but also different structures and some special cases and some other cases where we also need to look into vibration in more specific way, and that's what I'm going to share with you today. So the first case study that I will share is actually a set of staircases, and here we have very similar dynamic behavior as human excitation, as Gillian showed, but with a different view that we have to have in terms of how these will behave when people are going up and down. And in this case, for example, we have quite a big span, 11.4 meters, and we have two different sets of stairs. In this example today, we will show the conventional one, not the one where people are sitting, just because it can bring a real overview of how much you can improve the behavior and still save carbon. So let's get to it. So here is a bit of basis of design. It is going a bit further and on what Gillian explained, because she explained more related with floor vibration. And here we have the same concepts in terms of the walking force, but what changes is the frequency range of this walking force. Due to the going down and up, we have a different impulse. And also we have two harmonics, not four, and as we had in the previous analysis. It's also important to mention that the dumping for this case, these stairs that I will show are very low because they are steel stairs, but we have considered, the code advises us to consider something around 0.5%. We have considered 1% due to the handrails and the finishes on the stair, but it's a very important point because it changes a lot our results on terms of acceleration. And then here on the right, we have the acceleration criteria from SCI, and it actually just shows you an overview of what's acceptable, what is the human perception for different uses. And in our case, we have a light use for stairs because it is in an office building. So our target response factor will be around 32. So how do we start? We start by trying to make it work in our regular way with our structure and its element, and it's all related with the mass that Gillian has explained before. So when we try to make this stair working, of course, by ULS and SLS, the structure could be much reduced, but it doesn't work dynamically because due to its mass and long span and shape, it will actually vibrate when people go down. So we need to increase the members and make it much more stiff and heavier, so it would work by itself and people would not feel vibrations when going up and down. So in this case, when you look at it, we have a quite big profiles. So we have a frequency of 9.9 hertz and a response factor around 31, which is smaller than our criteria and our limit. So we would be okay on that, but we have a very heavy stair with 6,000 kilograms, and the utilization of the profile is quite low in ULS and on deflections because it's basically working and the design is driven by the dynamics. It's also very carbon intense. So how can we do to improve that and make a structure where we can have a lighter stairs but still functional on dynamic perspectives? We can actually count with technology a little bit and use a system of twin mass dampers. And here then we have the second, the optimized design, let's say like that, when we actually use a TMD system on the landing of the stairs. And in this case, we have we have higher utilization on the members because the member is smaller. They are more elegant, as the architects also wanted, which was one of the wishes of the architects. And if we look now for the response factor, accounting with the weight of the dumper, but not the dumper itself, we would have 277 response factor value. And of course, for you to design an element like this, when you have a different equipment, you need to align with the company. In our case, we have been always in conversations with Gerb, which is the company that supports us in Berlin, at least with this design. You cannot just design by yourself. You need to have this correlation with the different company that will support you on that. But this stair, for example, has much low carbon values, smaller elements, and the weight, as you can see, is basically 2,000 kilograms less than the other one. And we are going to have a further slide showing a little bit more in detail what we gain with that. But if we go now a bit on the response comparison between the two stairs to understand what happens that it works with the dumper. So in the first one, we have here the robust stair, which is with big profiles, and I wrote there what is the frequency of walking. And as you can see, since it has more mass, the peak of the response is actually between 4.5 and 5.5 hertz, which is outside of the walking range for people when going up and down stairs. And that's why it has a favorable result in terms of acceleration, because this stair has so much mass that the peak go outside of the walking frequency that will create a resonance. Although in the second one, when we have a much lighter structure, the peak would happen between 3.7, more or less, at 3.7 hertz, which means that when people walk on these stairs, they would actually feel the vibration. But when we implement a tuned mass damper system, you can bring this curve immensely down by the damping system. What you see there in this dashed line is actually just a prediction, because the final curve you could only see after testing the stair itself. But it would actually reduce a lot these curves, and then this acceleration would never go to that peak that would be without the damper. And here then we have a comparison in terms of carbon emissions and cost. And if we look at that, by the addition of the damper in this very simple staircase, we have a reduction of 28% in carbon emissions, and that is already accounting with the carbon emission of the damper system itself. So it is the complete system of the stairs, and the cost is around 10% reduction. So it's actually win-win in all situations, because you are saving carbon and you are saving also money normally for the client. And as the second study case that I want to show you, it's actually Südkreuz here in Berlin, and that was the inspiration of the architect. They wanted to build kind of forest of trees inside this atrium. It was an office building also, and these trees would be connected with different footbridges that are stairs at the same time due to the difference in the leveling of these trees. So if we look in a top view of this system when it became a real project, so you can see 4 of these trees that have different heights, and these platforms that are like footbridges and also stairs connecting each one of them. This system also serves as a lateral stability system for the stairs, and vertical due to the walking people and vibration that will be caused by people. And in this case, we don't have a final number between both systems, because it was so evident that dumping the system would improve so much the dynamic behavior in this case, that the first analysis were not completed to the detailed level, but you can see here some numbers that in the case without the dumping system, to keep the structure in a acceptable range of vibration, it would go around 200 tons of steel. And with the dumping system, a more refined detailed design, it was around 55 tons, which is a massive difference. Here then we have the execution, the construction phase. You can see the positioning of the dampers in the landing of each one of these stairs, footbridges elements. And of course, it's tuned after the execution, also after the finishing, so they can ensure that the accelerations will meet the criteria. And then here we have a final picture of the project after being done and in use. And that's actually a very nice case where you can reach all the goals, where the client is happy, the users are happy, the architects, and we have done the best job that we could as engineers, reducing carbon and increasing the the structure, usability, making it better to everyone. Yeah, I'll give back to Gillian.
That's my slides now sharing again. So what does the future hold? Well, serviceability design in all its forms will definitely become a far greater decider in our structural solutions with the drive to net zero design. Lighter, thinner and lower carbon structures are required to meet this goal, but are we suitably prepared for the implications of this? So our current design guides are based on research from over 20 years ago, and those design guides were never imagined to be used in the current landscape where you've got vibration serviceability being the key decider for everyday floor design. So as such, those design guides are now outdated. We saw from the case studies and the analysis studies that simple assumptions such as the levels of damping, the walking speeds, can have a massive influence on the predicted accelerations. So lightweight timber floors can be shown to give similar levels of vibration to traditional concrete and composite floors. But humans are sensitive creatures. Does a 6 Hertz resonant acceleration on a concrete floor feel the same to a human as a 6 Hertz resonant acceleration from a much lighter floor with additional damping? New guidance regarding mass timber structures tends to build off publications written for traditional materials, but is that the right thing to do? So research suggests there's an argument for using different acceptance criteria for higher frequency floors, so that those exhibiting a transient and pulsate response. But is there also an argument that perhaps different acceptance criteria are necessary for lightweight floors? The last thing we want to do as designers is to convince clients to build sustainable structures which don't perform adequately for the intended use once they're built. We're attempting to push the boundaries of design and whilst trying to understand the risks of our decisions. And that's impossible if we haven't got reliable guidance. The only way to facilitate greener alternatives is for all parties across the industry, so clients, contractors, manufacturers, consultants, and researchers, to work together as a united force towards a common goal, to carry out the necessary research, testing, and analysis to devise guidelines fit for this new era of serviceability design, so that we can move forward together as one to design better for the planet. So that's me finished. Thank you all very much for listening.